Alright, hello folks, and welcome to another episode of Redneck Academy. Today, we're going to start talking about Faraday's Law. So let's bring it back to the beginning. Back in 1831, a man named Michael Faraday made one of the most important discoveries that changed our world. So what he found was, if the flux linking a loop or turns of a wire varies as a function of time, a voltage is induced between its terminals. The second part states that the value of the induced voltage is proportional to the rate of change of the flux. Alright, so let's take a look at the equation that he formulated and postulated from his theory. So basically he states that the electromotor force is equal to the turns of wires times the rate of change of the flux. So basically, what we can break this down into, the EMF is pretty much just the voltage that comes from the flux changing over time with the in the wires. So when we look at this, the negative sign, it actually comes from Lenz's law, which says that the voltage induced opposes the change in flux over time. So basically, we're breaking this down even simpler. So we have the number of turns of the wires. We have the flux, which the unit is Webers, and we have time, which is seconds. So that's basically their formula. Alright, so now let's take a look at a practical example that is probably seen a lot in our daily lives. So basically, what you got here is you have a gas motor that's driving a shaft. And so now it's turning the shaft in the clockwise direction. So basically, you can say that there's a force coming off of this here wire. And because of these two magnets, you have a flux density that's moving from north to south. So now with force going up on this side, and we have flux density coming across, there's going to be a current induced in the wire. So the current then becomes induced in the wire, and because of the resistance of this wire, of this configuration, we get a voltage that's induced that is then read off that meter. So this is just a basic example of how electricity is generated. And without electricity, we can't do a lot of darn things. So basically, when you break this down very simply to its just circuit diagrammer, you got the voltage of the armature, or that wire that's spinning, and basically a current is induced because of our man Faraday's equation, which gives you your electromotive force, which we use to power a whole bunch of different things.
Okay, so now let's take a look at another example. So, as you see, as the wire goes into the magnetic field, a current is induced in the wire, but only when it's moving, because there has to be a change in flux over time for it to move. So you'll notice as it stops moving, the current induced goes back to zero. Another note to take is that this is creating a sinusoidal wave, because as the wire enters, it goes into the positive direction, and as it comes out, it comes into the negative direction. So what we so what we can see is that as the wire goes across the magnetic field, we get a current induced. So another thing that this animation is going to show you is the different ways that we can induce a current in the wire. Not the wire doesn't always have to be the thing moving. The magnetic field can be moving relative to the wire, and we'll see that a respective current is induced in the wire. So this is more like the example that we went over with the motor. As the wire is being rotated, a current is being induced in the wire. So I'll just let this play through its animation, and you can see the different ways that a current can be induced in a wire through a magnetic field. Thank you, and I hope you learned something today in Redneck Academy.